Good morning to all of you. In the last session, we have discussed the energy analysis for the control volume, in which we have discussed what is the work done or heat transfer in case of different processes, such as isobaric process, isochoric process, isothermal process, adiabatic process. Now, in today's session, we will do some more discussion on these control volumes. Okay. A control volume, as we know, is a fixed or moving region in a space where thermodynamic process occurs. It is bounded by a control surface which allows mass and energy to cross it. This concept is very much crucial for analyzing systems where mass flow occurs across the boundaries. Now, why this control volume analysis is important? Because in engineering, we have to analyze complex systems like turbines, compressors, nozzles, diffusers, and heat exchangers. These systems are integral to various industries, including power generation, aerospace, and automotive. So, as we all know, there are turbines, compressor, nozzles, diffusers, and heat exchangers. In the earlier session, we have seen that the turbines convert the kinetic energy into mechanical work. They are widely used in power plants to generate electricity. For instance, steam power plant in thermal power plants and gas turbines in combined power cycle plants rely on control volume analysis. And we have to optimize their performance in order to get a considerable amount of output in a reasonable input. Next is the compressors. Now, the purpose of the compressor is to increase the pressure of gases. They are used in refrigeration systems, the air conditioning units, and the industrial process. Understanding how compressor operates within a control volumes helps the engineer to design more efficient systems. Now, in case of nozzles, they increase the velocity of fluids while decreasing its pressures. They are critical in the rocket engines and jet engines, where the acceleration of gases is necessary for propulsion. Next is the diffusers. Diffusers increase pressure by decreasing velocity. They are used in wind tunnels to study aerodynamic effects and in jet engine inlets to slow down air before it enters the compressor. Next is the heat exchangers. They are used to transfer heat between fluids. They are vital in power plants for cooling systems and in refrigeration systems for efficient heat transfer. Now, in order to study the energy analysis or to study these control volumes, we have to extensively use the first law of thermodynamics. The first law of thermodynamics is a foundational principle that states energy cannot be created or destroyed and only converted from one form to another. This law applies universally to all the thermodynamic processes. Which are the thermodynamic processes? Just recall. In the last session, we have seen what is the isothermal, isobaric, isochoric process. So for this process, we can apply the first law of thermodynamics. Now, in case of the closed system, which is the closed system in which there is no mass across the boundary, no mass is coming inside or going outside the boundary. And for that, the first law is given by internal energy is the summation of the heat which is added into the system or the work done on the work done by the systems. Now, here, the first law ensures that the energy is conserved in all the processes. It is essential for understanding how energy transformation occurs in various systems, from simple mechanical devices to complex power generation systems. Now, in case of this control volume, when mass flow is involved, the first law is extended to account for the energy associated with the mass entering and leaving the systems. This extension is very much crucial for analyzing the systems such as turbines and the compressors. Now, the control volume analysis is a method which is used to study the thermodynamic process in systems where mass flow across the boundaries. Okay. Now there are two systems. One is closed system when where there is no any mass flow, and second is the control volume where there is mass is coming inside the system and mass is going out of the systems. Now in this case there is a term which is called as a control surface, which bounds the control volume, and it allows the mass and energy to enter and leave the systems. The control surface is the boundary of the control volume. It is not necessarily a physical surface but we can say it is a conceptual boundary that defines the system being analyzed. Mass and energy can cross this boundary, making it different from these closed systems. In control volume, mass can enter and leave the systems. This is in contrast to the closed system where no mass crosses the boundary. The mass flow rate is a critical parameter in control volume analysis as it affects the energy balance. Now there are different forms of energy in this control volume. So which are these? First one, we will start with the internal energy. And as you all know, this is the energy which is associated with the molecular motion of the substances. It includes both the kinetic and the energy and potential energy of the molecule due to intermolecular forces. Next is the kinetic energy. This is the energy due to motion. In control volume, changes in the kinetic energy are significant, especially in systems like nozzles and turbines. Potential energy is due to position or elevation. Changes in the potential energy are important in the system where there is a significant change in the elevation, such as the hydroelectric power plant. The flow energy is associated with the work required to push the fluid or out of a control volume. It is a critical component in the energy balance of control volumes, especially in case of these compressors and this pump. We will start the analysis of the control volume using the conservation of mass principle. The principle of conservation of mass states that the mass cannot be created or destroyed within a control volume. This principle is fundamental to analyze systems with mass flow. The conservation of mass is expressed as the mass which is coming inside the system minus the mass which is going out of the systems is equal to change of mass within control volume. The mass flow rate into the control volume is given by density of the fluid multiplied by velocity of the fluid multiplied by cross-sectional area of this conduct or the area of the flow. Now, in case of the steady state condition, the mass flow rate into the control volume equals the mass flow rate outside the control volume. This means there is no accumulation or depletion of mass within the control volume over the time. When we have to perform the energy analysis in the control volume, we have to use the energy conservation principle. The energy conservation in control volume involves accounting for all forms of energy transfer across the control surface. This includes heat, work, and energy associated with the mass flow. Now, There are certain mechanisms of the energy transfer such as heat, work, and mass flow. The energy transfer due to temperature difference is nothing but heat, and heat can enter or leave the control volume. The energy transfer through a force applied over a distance is work, and work can be done on or by the control volume. The energy transfer with mass entering or leaving the control volume is associated with the mass flow. This includes internal energy of the molecules, kinetic energy of the fluid, potential energy, and the flow work. And to analyze this energy balance, we have to use the equation of delta E is equal to Q minus W plus in bracket E in minus E out, where delta E is change in total energy within the control volume. E in is the energy entering the control volume with mass. E out is the energy leaving the control volume with mass. Now here Q is the heat added and W is the work associated with the control volume. Now there are different forms of energy such as internal energy. As we know, it is due to molecular motion energy. Kinetic energy is due to the energy of motion. Potential energy is due to elevation. Flow work is the work required to push the fluid in and out of the control volume. Now we will discuss the steady state condition. Steady state condition occurs when there is no accumulation of mass or energy within the control volume over the time. This means that the mass flow rate into the control volume equals to the mass flow rate out, and the energy flow rate into the system equals the energy flow rate outside the systems. In steady state condition, the properties at the point in the control volume do not change with the time. This simplifies the analysis of the system by eliminating the need to consider the changes in the internal energy or the mass within the control volume. Now, the steady state condition can be identified with the mass flow rate, energy flow rate, and the properties. So the mass flow rate should be constant, that is the flow rate into and out of the control volume. Constant energy flow rate in and out of the control volume to maintain the constant energy flow rate, and the properties at a point in the control volume should remain constant over the time. The examples of these steady state systems are the turbines and the compressors. They operate under steady operations. These devices maintain constant mass flow rate and energy flow rates. And heat exchangers with the constant flow rates, the heat exchangers operate under steady conditions, ensuring efficient heat transfer. Now we will see the energy equation for the steady flow. The energy equation for the steady flow in a control volume is a specialized form of the generalized energy balance equation. It accounts for the energy changes associated with mass flow and work done by the system. The energy equation for the steady flow is given by Q minus W is equal to mass flow rate in bracket change in enthalpy plus mass flow rate multiplied by change in kinetic energy plus mass flow rate multiplied by change in the elevations or the potential energy. So with help of this is a generalized steady state equation, and this can be used for analysis of the any systems which operates on the steady state conditions in order to identify what is the heat and work interactions of these systems. Now here we can see this enthalpy change accounts for the internal energy and the flow work changes. The kinetic energy is accounts for the change in the velocity, and the potential energy accounts for the change in the elevations. Now, there is certain common assumption or the basic assumption before applying this steady state condition. The assumption is that there should be no accumulation of energy within the control volume, which is consistent with the steady state conditions. Now we will see sample examples of the control volume systems. These are used in the wide range of engineering systems. Take the example of nozzles. As we all know, its function is to increase velocity and decrease pressures. And the system in which the nozzles are used, they are rocket engines, jet engines, and nozzles are the critical in accelerating gases to high velocities, which is essential for the propulsion. Diffusers are used to increase the pressure and decrease the velocity. Its application includes wind tunnels, jet engine inlets. Diffusers are used to slow down the fluids while increasing their pressures, which is necessary for the efficient operations in various applications. The heat exchangers are used to transfer heat between the fluids. Its application includes power plants, refrigeration systems, heat exchangers are the vital for the efficient heat transfer in many industrial processes. Now, the function of this turbine is to convert the kinetic energy into mechanical work. And these are used for the power generation in the steam and in gas turbines. These turbines are key components in power plants, converting the kinetic energy of the fluids into mechanical work that drives the generators. Now, in this slide, we will see the applications of these control volumes, such as in case of these power plants, as we have discussed, there are three important components in the power plant. One is the steam turbine, gas turbines, and the heat exchangers. In case of these refrigeration systems, there are three principal components where there is a steady flow energy equations we are using that are compressor, evaporators, and the heat exchangers. Now, in case of these aircraft engines, there are the jet engines and the turbofans, okay, and there are certain afterburners in which we have to use the steady flow energy equations. Now, in case of these automotive systems, we have to use this equation for the analysis of internal combustion engines and for the analysis of turbochargers and the superchargers. Now we will have concluding remarks on the today's sessions. We have seen the control volume analysis is a powerful tool for understanding thermodynamic processes involving mass flow. It is essential in engineering designs and optimization of systems like power plants, refrigeration systems, and aircraft engine. The principle of control volume analysis ensure energy conservation and efficient design, making them indispensable in modern engineering. Control volume analysis is crucial for optimizing the performance of the complex systems. It helps engineers to design more efficient systems by accurately modeling every transformations and the mass flow. Now, the advances in the energy systems, aerospace engineering, and automotive technology will continue to rely on the control volume analysis for the performance, optimizations, and innovations. As the technology evolves, the importance of control volume analysis will only grow, enabling the development of more efficient and sustainable systems. Therefore, now in this session, each content we have detailedly explained the concept, ensuring a comprehensive understanding of these control volumes and their application in thermodynamics. If you have any question or doubt, please feel free to drop me a mail. Thank you for your attention.